Okay, so here we go. Hi, Fraser. Hi, guys. All right, here we go. All right, so step one. You guys tell me, what's the first thing you always do with these things? Well, yes, read the question and then make a Freebody diagram. All right, so number 6, a box is placed at rest on a frictionless ramp inclined at 30 degrees. It's then projected up the ramp with an initial velocity of v0. The block experiences a drag force of blah, blah, blah. Solve it. Okay, so here we go. So, Freebody diagram. Here's the block. It's moving up the ramp with a velocity of v0. Hey, how are you? Good, thanks. All right. Oh, sorry, I got your foot there, Z. All right, so forces that we care about. Let's see, there's going to be force of gravity, perpendicular. There's going to be force of gravity parallel, right? I'm really unhappy with how I started this drawing. There we go. Okay, so FG parallel is just mg sine theta. FG parallel is mg cosine theta, yes? Is everybody cool up to there? Yes. Did I say it wrong? Sorry. Perpendicular and parallel. Let's see, what else? Ooh, it's frictionless. Yes. That's awesome. All right, so there's a normal force, which is going to be mg cosine theta. Now, because it's being projected up the ramp, which way is our drag force going to go? Down the ramp. And the problem tells us that our drag force is negative kV. So let's take a second now and decide which way we want to be positive and which way do we want to be negative.
Let's just make down.
So,
no, let's go negative is negative.
Yeah, I think most people are probably thinking up is positive, down is negative.
Yeah.
Great. Okay. So, again, it doesn't matter as long as you're consistent. Good?
Yes.
All right, so that's step one. Make a drawing. Am I missing anything? No. If there was friction, that would just be one more force that I'd have to deal with. Good?
Yes.
Step 2. Net force equals net force. So for us, MA equals FG parallel plus FD, right?
Yep.
Am I going too fast? Are we good? Okay, so now let's make some substitutions. A becomes dV dt. Okay. FG parallel is mg sine theta. Positive or negative? Negative, right? Because these are all positive values. So to indicate the fact that gravity is pulling it down the ramp, I got to sort of manufacture that negative sign. Good? All right? And then drag force is negative kV. Should the negative be there?
Yes.
K is positive. My velocity's up the ramp, that's positive. So to make my drag force negative, I got to put the negative sign in. Cool?
Yep.
Yes.
What if your velocity was negative? What would you make it?
Well, it's negative. Velocity was negative.
Yeah. That's cool.
So just stop and think through all of that.
Okay.
You good?
Yep.
Carla? Oh, I'm sorry, yeah.
If your velocity was negative, you're correct.
Oh, is that what you watch as the monitor?
Yeah, it's easier because when you stand in front of it.
Oh,
Oh, wait, that's actually a really good idea.
yeah.
Wait, so
Yeah.
that's where we stop during the test, or that's what?
So that's the halfway point.
Oh, halfway.
Okay?
Oh.
So remember, 2 parts. Step 1, set up a differential equation. That's it. Okay? So I told you this might be 10% of the, that's 5% right there. There's nobody in this room that can't do that. Yes?
I mean, that's 5% of the house.
50% of the time.
Oh. I was like, what?
Good? So yeah, so that's 5% of the test. That is good? Approximately. I'm saying that I'm going to make this drag force problem not worth a lot. So, are we good? All right. Step 2. Set up the integral. So, to set up the integral, you want to get all of your t's and dt's on one side and all of your v's and dv's on the other side. So, I'm going to give everybody a second to think about how they would go about that process. Don't overcomplicate it. Okay, so what I would do is multiply both sides by dt, and then probably just divide by the rest of that mess. So you're going to get m dv equals negative mg sine theta minus kv times dt.
The whole thing.
And so I think you just got to divide, but bring all that other stuff over, right? I don't know any other way to do it. What's up?
Parentheses around that. Because you.
Oh, yes.
Okay.
Is that what was bothering you?
Yeah.
Gotcha. You're right. You're right. Those parentheses are important. Okay, so let's solve it. So now we've got m over this big mess. Does anybody care if I bring the negative sign up front or up top and then do this? You guys see what I did?
Yeah.
All right. You don't have to do that, but just there you go. Good. Are there any problems with what I did there? Yeah, Adam.
So dv isn't divided by the mass because it's not really like there.
Say that again.
So dv isn't with the negative m being divided by like.
You could put the dv up here if you wanted. Doesn't matter. Is that what you're asking?
Well, like you don't have to put it there, but like it doesn't have to be divided by the negative mg sine theta minus kv because it's like there but it's not there.
Yeah, I mean this is basically what this means is you're multiplying by a very small change in velocity. So this expression says negative m divided by a big mess times some other thing. So if this was x, you could put it on top of the fraction or you could put it next to the
Oh
fraction.
wait, I'm done. Okay.
You know what I mean? It's just, treat it just like you would any other variable. Good? You're not dumb at all. It's freaking calculus, dude. Like, you're good. All right? Is everybody good? All right, so is everybody happy up to here? Molly, are you good? Where?
Well, that makes sense.
Because we're almost done. Is anybody confused about what I've done so far? All right, so now the last step is you just, I say just, and I know you guys are like, screw you, don't just say just. But you just take the integral of both sides. So watch. Take the integral of both sides. What is my time going from? 0 to t. What is my velocity at time 0? V naught. And at the end of time t, my v is vf or v of t. You can call it vf, I don't care. There it is. Now you're done.
Would you like us to take out the
That's it.
Okay, we can do that.
I know you can.
Would you like us to take out the constant?
All right? So what I'm saying to you is now you've got 4 months of calc to learn how to take this integral. Good?
So do we?
Is this manageable?
Can we do one on our own, like right now? Like as a class?
Are there other people that would like to do that? Take a minute to do that? How about, have we done number 5 in class?
Yes.
We haven't done number. Yeah, we did number 5.
Don't you have like random?
There aren't a ton of them. There aren't a ton because the only time you talk about drag force is when it's gravity. So it's either got to be falling or sliding up or down or in.
Well, Mr. Hacker, there has to be at least one other one that you have made in this class.
Right.
haven't seen yet.
How about we do one with friction? It's probably one with friction on an incline.
So incidentally, really quick, really fast, a quick comment. Listen, sometimes the drag force is kV. Sometimes it's kV squared. That doesn't change anything. Look, kV squared, kV squared, kV squared. Okay, you still solve it the same way. All right, I'm thinking right now about an example I can give you.
Can we do a falling one where it's not on an angle?
That's what I'm trying to figure out. But I mean, so there's not a lot to that. I mean, that's because then there's just gravity and drag force. You know what I mean? So I'm trying to come up with an example where there's gravity and maybe something else. So give me a second to think. Yeah.
A guy or
But, would it be okay if we left the t, or the integral of dt, or t, whatever, as just t?
Sure. Like take it one step further.
Yeah, just
Yeah, that's fine. Yeah, yeah,
Like
yeah.
us to both.
Yeah, if you know extra calc and can go beyond this or simplify this in other ways, badass, do it up. No. No, because that's not fair to the people who have not yet had to come up with 3. All right. Everybody good? All right. So, how about this?
I like it.
All right, so that's a vertical line. All right?
Sure.
Here's a box. All right? It's got a little rocket pack on it. So the rocket pack is pushing it this way with a constant force of F. This is not bad. Some of you guys are like, screw you, it's not going to be bad, I promise. All right? So we got a constant force of F pushing it that way. All right? It's not enough to prevent it from sliding down the ramp. So it slides down the ramp. Coefficient of kinetic friction is mu k. Okay? Drag force as it slides down the wall is kV squared. Okay? So, does everybody understand what's happening? You've got this thing being pushed against a wall. There's not enough force, so it slides down the wall. So, write a differential equation which could be used to solve for the velocity of the block at time t. That's question A. Oh, the block has mass m. It's sliding down the wall. It's this. It's this, you guys. So my hand is a rocket. Okay? Gotta make sound effects or it doesn't work. I want to hear a lot of ing. Alright, I'm going to pause the recording. That was good. That was good rocket. Sorry. Okay, so we got the force. We got the force this way. Normal force pushes back to the left. Is everybody okay up to there? Yes. Alright, what other forces are there? Force of gravity. What kind of friction? Kinetic and drag force. Good? All right, now let's do it again, but with names. F is F. How big is my normal force? F. Right? Why? Because it's not moving horizontally. Good? Fg becomes negative mg. Good. I like the fact that somebody said negative. Because it's pulling down. Force of kinetic friction is going to be mu k times F. Right? Because F is the same as my Fn. And then there's drag force. Good? So there's your free body diagram. Is everybody good with that? Okay, so here we go. Net force equals net force. MA equals negative mg plus mu k times F plus kV squared. Problems? Oh, Oh, shoot, I'm sorry. I told you I was going to stop after we did the free body diagram. Sorry.
It's okay.
You want me to give you a minute to keep going? Okay, take a minute. See if you, so, getting the differential equation from here is easy. So see if you can get through to the integral. Because yeah, never mind. Good?
Should we assume that it's sliding down already with the velocity of v naught?
No. Assume it starts from rest. Thank you. Assume it starts from rest.
You need to take the integral.
Okay, so, I'm sorry I jumped ahead. I told you I was going to give you time to work. Does everybody get up to here?
Yeah.
Net force equals net force. Next step,
Make the A different.
make the A dv dt, and you're done, right? So that's... Guys, quiet, please. All right, are we good up to there?
Yes.
All right, so that's half, right? So the problem A is going to say, write a differential equation that can be used to solve for the velocity at time t. There's your differential equation. Are we good with that?
Yes.
All right, next step.
Multiply by dt.
Get all of your t's on one side and your dv's on the other side. So I'm going to kind of do this all in one big thing. We're going to multiply by dt and then divide by this big mess. Is that cool? So I'm going to get m over that big mess. You have to stand like this when you integrate, you guys. It's a rule.
Full attention.
Does that make sense? I'm always super self-conscious when I write low down on the board like that. Does everybody get up to there?
Yes.
Aw, it's okay, Mr.
Everybody's happy?
Yeah. Sure.
All right, so now, what's the next step? You just integrate. You have to say just.
All you need to do is integrate.
All you got to, all right, so squiggly line, and now what? Set the bounds. Time goes from 0 to t. Velocity goes from whatever v naught is. I told you here it was 0 to v of t. There you go. You're done.
If you tell us the velocity and we put v0,
Say that again.
give us the velocity and we put v naught. So you can't keep
Technically, yeah. I don't know if I would take points off
You
at
could-
this point, but
Yeah, you could keep.
Molly, guys, quiet, please.
On the test, can we just, do you want us to like write that as a whole other step, or can we just throw?
You can just do what I did there. That's fine.
Would you like us to take the constant?
Eventually, you're going to want to do that at this point. That's all calc stuff. Let's just get to this point, and then you guys will learn how to deal with taking the integral later on in your calc class. Good? Manageable? All right, excellent. What else do we need to talk about? What other problems did we have questions with?
Maybe like
What's on the test? Someone should take one of the tables and come in and steal it.
Wow. Bold words.
We can lure him outside
Yeah.
of the room. Daniel.
what?
Yeah. Okay, guys. Shh. So there was a request. There was that extra sheet that I told you guys about, right? Remember that last page that never got passed out somehow? Do I have a copy of it laying around? Probably not. Let me just pull up the worksheet. AP worksheet, chapter 4. Who said that? Which one? 13. A block slides. This guy?
Yeah.
Oh! Shoot. Darn it. Never mind. Okay. Nothing. I forgot to do a thing, but I think it's too late at this point. So. Yeah, so that thing that I just was talking about, whoever's mumbling and grumbling, I won't put it on the test. So chill.
Initial speed of
Okay, so this was one of the problems that was on that last sheet that I told you guys yesterday you could/should look at. So it says a block slides with a constant velocity down an inclined plane that has a slope angled theta. The block is projected up the same ramp with a starting speed of v naught. Question A, how far up the plane will the block move before coming to rest? And then after it comes to rest, will it slide back down again? Okay, so here's our drawing. So let's give this block a mass of m. The plane is inclined at an angle of theta. It is fired up the ramp with an initial velocity of v naught. What should I do? Draw a free body diagram. So let's see. So gravity gets replaced with mg cosine theta for my perpendicular component, and mg sine theta for my parallel component. Okay, what else? Normal force. All right, everybody good up to there? Let's see. There's no friction. Do we know that? I guess we have to. Wow, it doesn't say it explicitly, does it?
Well, it says slide. It's everything.
Well, you could slide and still have friction.
Yeah,
Wait a minute, hold on. Something's wrong here.
It slides down with constant velocity.
Oh, yeah.
Oh, I get an F minus. Sorry, I didn't read the problem right. Sorry, I was trying to hurry. All right, sorry. So there, gotcha. So it says a block slides with constant velocity down an inclined plane. So why is that information important? There has to be friction, right?
Oh, yeah.
Because otherwise, if there wasn't friction, it would be accelerating, right?
Or the incline is 0 degrees.
Or the incline is 0 degrees. All right, so are we good so far? All right, so what this is telling me then is my force of friction kinetic has got to equal mg sine theta.
That's right, accurate. It like lights on the other side of the board and then disappears. Like when you write on the ghost right.
Oh, that's weird. Huh. Okay, are we good with this?
Yes.
All right, so I feel like I can use this to find something out. What should I probably use this information to find? I also know another expression for my force of friction, don't I? It's also equal to my coefficient of kinetic friction times my normal force. Is everybody good up to there? All right, so what I know now is mg sine theta is equal to mu k times mg cosine theta. So the mg's cancel, and you get mu k equals sine theta over cosine theta, which is just tan theta, right? Do we know the angle? It's just theta, or there's literally no numbers. Okay. All right. That's okay. So, are we good up to there? All right.
His flow is literally on parallel. Never seen somebody short
How far up the plane will it go when it's sliding down?
Can you give
That's just...
Ew. All right. Is everybody good with what we've done so far? Okay. All right. So that's all the information we can get from it sliding down the ramp at a constant velocity. Is everybody good up to there?
Yeah.
All right. So now what happens is we're going to take this same block and we're going to project it up the ramp with a starting velocity of v naught. Okay? So let's do that. So here's our block being fired up the ramp now with a starting velocity of v naught. It's got a mass of m. I know that there's an mg cosine theta here. I know that there's an mg sine theta here. I know that there's an mg cosine theta here, Fn, Fg perpendicular, Fg parallel, and what other force? Kinetic friction, right? So let's see, kinetic friction. There's a couple ways we could express this. I mean, I guess we could write it in terms of tan theta times my normal force, but that feels needlessly complicated. Right? Don't we know an expression. Oh, we know our force of kinetic friction is this, and that doesn't even use mu. So I guess I sort of jumped down that road. Let's find the kinetic friction coefficient, but I think we don't really need it. Because I know this is my force of kinetic friction, right? Does that make sense? Oh. I am making a sudden realization. mg sine theta. I'm falling. Carla, what's up? We are looking to figure out how far up the ramp it's going to get.
So it's going up the ramp?
Yep, it was projected up the ramp at a velocity of v naught.
Has it always been going up the ramp?
There were two parts. So the first part was
I just figured that out.
it slides down the ramp at a constant velocity.
Okay.
All right, that information was given to you so that you could make the realization that I was a little slow making, which is that the force of kinetic friction is going to be the same as your Fg parallel. Good? All right, so now our block is sliding up the ramp, and so here's what I know. So, is everybody okay with the drawing I've got so far? Any questions? All right, so look, net force equals net force. MA equals, what's my net force going to be, you guys? 2 mg sine theta. Right? Because you've got 2 mg sine thetas pulling it down the ramp. One from gravity, one from friction. So all that business I did about finding the coefficient of friction, we didn't actually need to do. Follow? All right, cool. Boom. Boom. Now I know my acceleration. And the question wants to know how far up the ramp it gets. So let's make a list of the things we know. We know A. We know V naught. What's VF? 0. And we're looking for displacement. So I'm looking at 2A delta x equals VF squared minus VI squared. Or delta x equals VF squared minus VI squared all over 2A. Let's plug in our numbers. VF is 0. VI is V naught. All over 2 times our acceleration, which is 2g sine theta. And I missed the negative sign. Right? My net force should have been negative 2 mg sine theta, right?
No, shouldn't V naught be squared?
Oh, I forgot the squared also. Sorry, I thought you were asking for the negative. All right, and then the 0 goes away, right?
Where do you get the negative?
Because both gravity and friction are pulling the block down the ramp, so those both have to be negative quantities. Good? That's that. There's a lot going on there. That's a tough problem. Adam, yeah. You sure?
Yeah.
Okay. All right, is everybody good? All right, now, once it gets to the top of the hill, it's going to stop, right? This is the last question. This is important. Please hear this. Once it gets to the top of the hill, it's going to stop, right? So here it is. It's at the top of the hill. For a brief moment, the velocity is 0. You're going to have the force of gravity parallel pulling it down. Is it going to start coming down the hill again?
No.
A lot of people are saying no. Can somebody give me a good reason for why? Sure, we got that.
If the coefficient of static friction is greater than the coefficient of kinetic friction, then it won't slide down because it's the force of gravity parallel to the slope is equal to the force of kinetic friction.
Perfect. Yeah, so what Jen is saying is we already know that the force of kinetic friction is equal to the FG parallel, right? How does static friction compare with kinetic friction? It has the capability to have more static friction than kinetic, right? Your FFS max is at least as big as your FK. So if kinetic friction can make the net force 0, then absolutely static friction can do the same thing. So it will not slide back down the ramp. That is important. Okay? That exact concept came up on 2 other problems that, or at least 1 other problem that didn't get discussed. Nobody asked about it. But okay. So Hunter, you just said you wouldn't have thought of that. Good trick to know. Okay. I don't know that it's on the test, but it's a good thing to know. Okay. Anthony, and then Molly.
If they're like both, if they're the same and the net force is 0, does it move? Okay.
No. Yeah. No. So it would come to a rest and then just stay up. Good. Molly.
Why did we use static? Well, in the second part, it was sliding, so we used kinetic.
Yep.
So we just maintain using kinetic because it was sliding in the second part.
Exactly so. Yeah. Does that make sense? All right. What else, you guys?
Can we do like a hard basic problem?
That, to me, that was a hard basic problem.
No, I meant like from 4-1. I feel like we're gonna.
Oh, I gotcha. Sorry. Whenever you say basic, I always assume you just mean something that doesn't use calculus, which maybe I shouldn't do that. Yeah, I don't know. I don't know.
Turn this car around.
Do you have a request, Sebo? I'm not. Thank you. Okay, so let's do this. So Roy's got a mass of m. All right. The elevator is going to accelerate upwards, so it's going to gain vertical velocity. Let's have it go. I'm trying to think if I can come up with an example with no numbers or not. I know, right?
That's
I think I got to do numbers here. So let's have it accelerate from rest to, I don't know, final velocity of, let's say, 8 meters a second. We'll keep the numbers easy. In a time of 2 seconds, say. Find the ratio between the normal force and the force of gravity. Find the ratio between the normal force and the force of gravity. There you go, no numbers. These problems are hard to make up on the spot. You're finding the ratio between the normal force and the force of gravity. So we got a dude standing in an elevator. The elevator is going to begin moving up at a preposterous speed of 8 meters a second. Which is like 20 miles an hour, so it's a pretty fast elevator. And this all happens in 2 seconds. So yeah, it's like the one that takes you to the top of the Empire State Building or something. The Sears Tower that's no longer called the Sears Tower. The Willis Tower. Still mad about that. Looks like he's what? Holding it down. So you're looking, once again, you're looking for the ratio between the normal force and his weight. Normal force and his weight. Normal force and force of gravity, I think is what I said the first time. It's the same thing, right?
Normal force is weight.
What?
Didn't you say normal force is weight? If you're not moving,
If you're not moving vertically, then your normal force will equal your weight. But if there are any other vertical forces or there's vertical acceleration, then the normal force and weight are not equal.
Gravity and acceleration.
All right. I'll give you another minute or so, and then we're going to run out of time, so I want to make sure we have time to go over this. Okay, let's do this then. Everybody had a minute to at least figure out if they know how to do it or not? Okay. So what forces are on him? Gravity. And the normal force. I think that's it, isn't it? The normal force is the floor lifting him up, right? That's why you feel heavier when the elevator first starts moving up, right? Because there's extra pressure on your feet to lift you, right? Okay. Why did I give you all this garbage? Find the acceleration. So do it. Your acceleration turns out to be 4, right? Good. Giant, super huge, important rule. Well, okay, so cool. Net force equals net force, right?
Yep.
So, MA equals FG plus FN, right? So, M times 4 equals negative M times 9.8 plus Fn. Agreed?
Why is gravity, the force of gravity, not negative there?
Here?
Well, no, never mind, negative. Sorry.
I mean, the arrow points down. I mean, yeah, you could put a negative there. Is that what you're asking?
Yeah.
Yeah, I probably should have put a negative there.
Okay.
Good?
So it would be negative M 9.8.
So it looks to me like Fn is going to be M times 4 plus M times 9.8, right? Which is M times 13.8, right? So that's 13.8 M, right? So that's my Fn. Let me pause there for a minute. Did I lose anybody there? All right, so the question didn't ask for the normal force. It asked for the ratio between the normal force and force of gravity, right? So Fn over Fg then is 13.8 M over 9.8 M. M's cancel, and there's your ratio. Where's her weight? What's the definition of weight? Carla, do you remember? Force of gravity. Weight is force of gravity. Yeah, but the M's are going to cancel. Is that what you're asking, or no? I said find the ratio between the normal force and the weight, not the normal force and the mass. Good? All right. Hey guys, quiet please. We still have a few minutes. Jill! Sarah, what do you got? I don't know. Why? I don't mean that in a snarky way. There isn't one. So here, listen you guys, this is a really good question with a pretty quick, simple answer. Tension, you're right. It's been at least a few days since we've done a tension problem. If I had said, instead of having Roy standing on the floor of the elevator, suppose I had him hanging from a rope in an elevator, and said find the ratio between the tension and the force of gravity, then it would be the exact same thing. Do you know what I mean? The idea is the tension holding it up, behaves exactly the same as a normal force holding it up. Good? So it doesn't change how you solve the problem. Cool? All right. Oh, thanks. All right. I'm around after school if you need it.